So thank you very much. It's a pleasure to make my annual pilgrimage. And I'm going to talk to you about work that I originally came here on a 2-3 year postdoc to work with George Smoot on back in 1997. And here we are today, probably about halfway through this project now. So I wanted to give you a bit of a context, a brief history of cosmology. The nice thing about cosmology is, as a science, it's only 100 years old, less than 100 years old, so it really can be a brief history. I want to talk to you a little bit about CMB physics and what we're trying to do with the CMB, why, there's some motivation for it, and then the analysis of CMB datasets and why that is a high-performance computing challenge, has been, is, and will continue to be for the foreseeable future. But there is an important caveat. Everything I say may be proven completely false. Often in error, but never in doubt. Lev Landau coined this very nice characterization of scientific cosmology. So as I say, cosmology is less than 100 years old, and in some ways you can trace the beginnings back to general relativity, so 1916. Einstein makes this extraordinary breakthrough and decides that yes, space tells matter how to move, and at the same time matter tells space how to bend. And we have this beautiful equation, very simple compact form to write down, extraordinarily rich and complicated and very hard to solve. On one side we have space, on the other side we have matter. So we have the Einstein tensor, the Ricci tensor, and the curvature term bundled up into that g mu nu, and on the other side we have the energy momentum tensor. Lovely equation, but Einstein obviously immediately realized that one of the implications of this is that the universe is dynamic, and that can't possibly be the case. Everyone knows that the universe is static, at least in 1916 everyone knows that. Remember, often in error but never in doubt. So we have to fix this. We can't have a dynamical equation for the universe, so let's stick in a fudge term. And so Einstein adds lambda g mu nu, to the equation, to general relativity, to make it a static universe. Even though this is only static because we're in an unstable equilibrium. So even the slightest perturbation about this would cause the universe to start, would cause some dynamics, would cause some motion to start, and that would drive it further from the equilibrium, and you get a runaway. So we have a fine-tuned, you have to take a very, very particular value of lambda, unstable equilibrium. Now, of course, one of the reasons Einstein gets away with this, at least in his own mind, is that he doesn't believe in anything quantum. He's ultimately the last great classicist. So in some ways, unstable equilibria, well, that's just the way it is. Of course, if you have any quantum behavior going on, then an unstable equilibrium is a no starter. So here we have the equations of general relativity for a nice static, albeit unstable universe. Now we move forward a decade or so, and Edwin Hubble is using the 100-inch telescope on Mount Wilson to look at what then were considered distant galaxies. And so he looks at these galaxies and he measures two things about them. He measures their velocity using their redshift, so how much is the light stretched. And he measures their distance using something called Cepheid variables, which are variable stars whose periodicity is tightly coupled to their absolute brightness. And if you know the absolute brightness of something and you measure the apparent brightness of it, you can tell how far away it is. It's a standard trick in astronomy. So he measures these velocities, he measures these distances, he plots them on a graph, and lo and behold, the velocity is proportional to the distance. Well, actually it isn't quite. If you look at Hubble's original diagram, most of the galaxies he's measuring are very close by. Most of them are dominated by their motion in the local group. So he's really got just the very beginnings of the Hubble diagram, and it's one of those things, it's one of those Rorschach tests. You can basically put a line anywhere and say, look what I found. So, but it gets plausibly a linear relationship, and as more data are added, it gets more and more obvious that this is what's going on. As you get to further and further galaxies, you're less and less impacted by their local motion and more by the global expansion of the universe. But the bottom line is he shows that space is expanding. It's the immediate naive assumption is, oh, well, we're sitting in this very privileged place in the middle of everything. Everything's rushing away from us, but it doesn't take a lot to realize that wherever you are in the universe, in an expanding universe, it's going to look like the universe is expanding away from you. So the universe is dynamic. And Einstein slaps his head, realizes he could have predicted this from general relativity, and calls the cosmological constant his greatest blunder. As we will go on to see, it's now considered to make up about 70% of the universe. So if your greatest blunder turns out to be 70% of the universe, you're doing pretty well. So then we have this dynamic universe. So the question is, well, it throws up all kinds of questions. It throws up questions about beginnings, ends, what's going on in the universe, what's happening as this expansion is happening. And we end up with two camps. We have the steady state theorists who argue that, well, the universe is expanding, and that expansion is just causing new matter to be created to keep the density constant. So you stretch the universe, and the energy that's doing the stretching somehow generates new matter to fill the empty space. The universe is as it is, always has been, always will be, unchanging, no beginning, no end, everything steady. Not very popular outside of cosmology. The alternative theory is the Big Bang theory. The universe is created in some moment, and by the universe we mean the matter, the energy, the space, and the time. The question, what happened before the Big Bang, doesn't make any sense because the Big Bang is the beginning of time. So you don't get to say there is no before in that sense. Of course, you can't poke too hard at those questions because they unravel fairly rapidly. But we would then predict that we have this expanding, rarefying, cooling universe. So it's getting bigger, less and less dense, cooler and cooler as everything is stretched. And there are these two theories, and there's very, very little observational evidence in cosmology at this time. We're talking about an epoch where in astronomy as a whole, a population of a dozen objects was considered a really good sample. These are just hard things to observe outside of our galaxy, so it becomes something of a philosophical debate. But we do get one very interesting prediction that, of course, is predicted and then immediately forgotten for 20 years, which is that if you have an expanding, cooling universe, then at some point after the Big Bang, you will drop through the ionization temperature of hydrogen. So earlier than that time, protons and electrons are kept apart. If they ever try and form together into hydrogen atoms, they're ripped apart by the energies of other photons smashing into them. So it's just this big plasma soup. Fall through the ionization temperature, the protons and the electrons combine to form hydrogen atoms, and suddenly there's nothing for the photons to bounce off. Prior to that time, they were bouncing off the electrons like crazy. Suddenly, there are no free electrons. They've all been sucked up by the protons, and the photons just free stream. Whichever direction they were moving in, they just carry on in that direction for the rest of time, more or less, and we'll come to the more or less later. So we're sitting in the middle of this diagram, in the middle of essentially a neutral universe. Well, it's been subsequently reionized, but at a level of a density that's so low that there's still very little to hit. And we look out in space, we look back in time. Eventually, we look back to this moment of what we call recombination, which is a misnomer because it's the first combination that ever happened. So it's really the moment of combination. And those photons that happen to be moving in our direction at last scattering are the ones we see now. Wherever you are in the universe, you look out in space, you will see those photons that were traveling in your direction at last scattering. So this is, again, not a privileged position. We're not going anti-Copernican. We're just sitting, looking out in space. We would see the same thing wherever we looked from. And Alpha, Herman, and Gamow predicted this in 1948, wrote a very nice little monograph and predicted that you would end up with a residual photon field from the Big Bang somewhere between 5 and 50 Kelvin. Again, not really taken very seriously because at this point, cosmology is less than 50 years old and there are still plenty of people who don't even think it's a science. So this gets called the cosmic microwave background. Well, cosmic because it's filling all of space. Microwave, this is the characteristic temperature. So the characteristic temperature is taken from, take the ionization temperature of hydrogen, about 6,000 Kelvin, 3,000 Kelvin, and then stretch it by the expansion of the universe between last scattering and today. It's about a redshift of 1,000. Wavelengths expand by a factor of 1,000. Temperatures drop by a factor of 1,000. So we go from 3,000 Kelvin to 3 Kelvin. So 3 is in the 5 to 50 range, given the precision of cosmology in 1948. And background, because these are the primordial photons. These are the photons generated in the Big Bang. So these are the photons coming from behind everything, all of the things that astronomers and astrophysicists are typically looking for. So one of the ways I sometimes like to describe it is that the rest of astronomy is looking at the furniture and we're looking for the wallpaper. So this is the stuff behind. And the extraordinary thing about these photons and why they've turned out to be such a rich source of science is that these photons have seen the entire history of the universe. Everything that has happened in the history of the universe has left its imprint on these photons. They're created in the Big Bang. They run through that whole early history, having all kinds of, everything that goes on prior to last scattering leaves some imprint. They hit last scattering and then they free stream to us. We used to think of it, that was the end of it, and they free streamed without any perturbation. But now we know that there are very, very subtle perturbations that go on between last scattering and us. They get lensed by galaxies. They get upshifted by time-varying potential wells. They can hit very hot patches of gas and have their spectra shift slightly. And all of these second and third order effects we're now beginning to measure and use these photons as a trace through the entire history of the universe after last scattering as well. So basically, the whole history of the universe is encoded in these photons, if only we can get that signal out. So 1964, Penzias and Wilson are working at Bell Labs, and Bell Labs have a nice big radio telescope that was used for all kinds of activities, things that humans want to do with radio waves, and then it was considered sort of surplus to requirements. So they figure that they'll see if they can do some nice radio astronomy with it, to look at some galaxies and things. So first thing to do when you've got a new telescope, you want to set the zero. So they pointed at a part of the sky where they know that there is no radio signal. No one's ever seen anything in the radio spectrum in this patch of the sky, and they can't get it to zero. They try day versus night, they try summer versus winter, they try all the systematics tests you could think of. They determine that it's not an instrumental effect. In their paper they discuss the need to remove a white dielectric substance left behind by the pigeons that were roosting in the telescope. That's what graduate students are for, to climb inside that thing and scrub it out. Couldn't get this signal to go away. Meanwhile, down the road, Dickey, Peebles, Roll and Wilkinson were trying to build exactly this kind of apparatus, but they're doing it on a university budget, not a Bell Labs budget, so this is obviously a fairly substantial piece of apparatus. And someone realized that the two had something going on and got Penzias and Wilson to give Dickey a phone call, and as law has it, he was in his office with the gang and they were discussing how to move forward, and he got the phone call, and after the end of the phone call, hangs the phone up and says, "Boys, we've been scooped." So Penzias and Wilson had completely accidentally and unintentionally found the signal that was to win them the Nobel Prize in 1978, while Dickey, Peebles, Roll and Wilkinson got a pat on the back and got to write the companion paper explaining what it was that Penzias and Wilson had seen. And what it was the microwave background at around the 3 Kelvin as predicted. So that gets us up to the 60s. We then have we have decades of more and more refined instruments making more and more precise measurements of this. And one of the funny things that comes out of this is that it turns out that this signal is incredibly uniform across the sky. And so in some ways exacting their revenge, the theorists keep telling the experimentalists, just get one more order of magnitude more sensitive and you'll see something. And so the experimentalists work like crazy and make a slightly more sensitive detector and do their measurement and see nothing, no variation, and so, oh, well, we forgot this term, one more order of magnitude. This goes on several generations, and we get to this 1 part in 100,000, that this temperature of the Big Bang is uniform across the sky. And that's a big problem. In a Big Bang cosmology, any points more than about a degree apart on the sky were out of causal contact at the time the microwave background was last scattered. The universe just isn't big enough, the causally connected part of the universe isn't big enough to encompass points more than a degree apart. So why are they at the same temperature? This is a big problem, and you know, again, we're cosmologists, so we sweep it under the rug for a while and let it go away. But it just won't go away, and there are other issues that come up with this as well. Why is the universe so close to being flat? So if it's exactly flat, it will stay exactly flat. That's the overall geometry of space-time. Is it Euclidean or non-Euclidean? But if you're slightly away from flat, one side or the other of flat, if you're open or closed, as the universe evolves, you'll be driven further and further away from flatness. So why are we so close to flatness at this epoch? And where are the magnetic monopoles? At this point, we're all into quantum field theory. We know that we've got this wonderful quantum chromodynamics that explains 3 of the 4 fundamental forces. But we know that during the evolution of this quantum field theory, it goes through various spontaneous symmetry breakings, and that's what separates the 4 forces, or the 3 forces that QCD describes, from each other. And in those transitions, you should expect to generate kinds of topological defects, the little knots of energy where the field orients in the field orientations after the symmetry breaking don't match up, and you get a trapped region. Magnetic monopoles are one example of this. The universe should be full of them. It clearly isn't. So where did they go? So it turns out that Alan Guth and others, but he certainly wrote the most influential first paper on this. So he proposes a very, very early period of exponentially fast expansion, inflation. So the radius of the universe goes from something very small to something very large very quickly. And essentially this is superluminal expansion, but it's okay because it's not something moving faster than light, it's space expanding faster than light. And that's completely fine with relativity. You can't move faster than light, but there's no reason why space can't expand faster than light. So that takes a small, causally connected region with one monopole at most in it and expands it to the size of the entire visible universe. So that deals with your monopole problem, that deals with your horizon problem, and it deals with your flatness problem because that expansion drives you arbitrarily close to flatness. And so all the subsequent move away from flatness could still leave us this close. Yes?
You said space can bend faster than the speed of light?
Space can expand faster than the speed of light, yes.
Is there a proof of that? Or like
there's nothing to constrain it. So the reason we think of the speed of light as being a limiting factor is from special relativity. And in fact, even in special relativity, if you're moving slower than the speed of light, you can never reach the speed of light. If you're moving faster than the speed of light, you can never reach the speed of light. So it's really just a boundary that you can't cross. But that is for matter or energy moving through space. And what we're doing in this case is just stretching space. Obviously. So now we've exponentially expanded our universe. We've got rid of the flatness problem, the horizon problem, the monopole problem. We've got this enormous universe that's come from a tiny, tiny region to begin with. But now we have the sort of the converse problem. We've generated this extraordinarily flat, uniform, visible universe back at the beginning. Great. Except if we look around today, the universe is not extraordinarily uniform on anything but the very, very largest scales. So where do these superclusters of galaxies and clusters of galaxies and galaxies and stars and planets and things come from? How do you get all this inhomogeneity in this spectacularly homogeneous beginning? Now you've inflated everything and flattened everything out. So there has to be some seed perturbation around which everything else is going to collapse. And if that's true, then that seed perturbation must leave an imprint on the microwave background. So regions that are slightly more dense should be slightly hotter. Regions that are slightly less dense should be slightly cooler. So we should see this pattern of hot and cold spots in the microwave background. But what we see when we look at it is that it's completely uniform to 1 part in 100,000. So you just have to go get more sensitive. You better find these somewhere. And so finally in 92, the COBE satellite and George Smoot finally detected inhomogeneity in the microwave background. It was very much a statistical detection. The pattern of blobs you see behind you is all instrument noise. It's only when you take the angular power spectrum of these blobs that you actually see something that's different from the visual impression, which is somewhat misleading there. But so we finally see that yes, there are these tiny variations at the 1 part in the 10 to the 5 and smaller in the microwave background. Incidentally, on the same satellite, the second experiment shows that the CMB is as near as we can see a perfect black body. Again, something that you would expect for a signal generated from the Big Bang. And so John Mather, who ran the black body spectrum part of the experiment, and George Smoot, who ran the anisotropy detection part, they get to share the 2006 Nobel Prize. So there's 2 Nobel Prizes for the CMB work.
Can you explain again? Could you explain again? Okay, so if there are density perturbations in the early universe, what structure again?
So those, because gravity is a one-way force. If you have a slightly overdense region, it will suck more matter towards it. It'll become more overdense. It'll have a stronger gravitational field. It'll pull even more matter towards it. So you get a runaway gravitational collapse around these little seeds. But for that to happen, there has to be some seed for the collapse to start happening around. Once it starts happening, it's a runaway process. It only goes one way, at least until the first stars light. But you need something to seed it. So there have to be some seed density perturbations, and if there are seed density perturbations, they should show up in the CMB. Because if you've got a slightly denser region, it's going to be slightly hotter. So when we measure the temperature of this background, there should be hot regions will correspond to overdensities, cold regions will correspond to underdensities, or vice versa. If there are overdensities, they will show up as hot spots. If there are underdensities, they'll show up as cold spots. So what we're saying is both overdensities and underdensities must exist for there to be structure today. Therefore, we must see them in the CMB. Why couldn't we? Well, we just weren't looking hard enough. And so in 92, we finally have a sensitive enough experiment. Involves going to space to get above all the atmosphere and issues that involves. We can scan the whole sky from space, and we see the first traces of those perturbations. So everything is fitting very nicely. We have a very compelling cosmological story. Everything falls into place. There are a few details around the edges we're not sure about. Cosmology in the 90s is still a field where a factor of 2 is considered precision. So the expansion rate of the universe is somewhere between 50 and 100 kilometers per second per megaparsec. Interestingly, it's a bimodal distribution. There's one camp that's absolutely it's 50, and there's another camp that's absolutely it's 100. Turns out it's somewhere in between those two, but so at this point we're still interested in things like the fate of the universe, the geometry of the universe, still studying, and in particular the relationship between the geometry of the universe and the amount of matter in the universe was considered to be a cause and effect kind of thing, that if you had more than there was a critical density that gave you a completely flat universe. If you had less than that amount of matter, the universe would be open and would just carry on expanding forever. It would slow down, but it would never stop. If you had more than the critical density, the expansion would eventually stop and you'd get contraction starting. The gravity would win. And if you were exactly at the critical density, then the universe would come to a halt in infinite time in the future. So there were these three cases, and the fate of the universe and the amount of matter in the universe were completely tied together. Wrong. Saul Perlmutter and co. and the Adam Rees and Schmidt, two separate experiments, but Saul Perlmutter leading the group at Berkeley Lab, started measuring the brightness and distances of supernovae, so very similar to the original Hubble diagram work. And so here they're observed brightness versus redshift. Remember, those are proxies for distance and velocity. Hubble's original work was down in this corner. But this has now been pushed out with these very distant supernovae. Obviously, supernovae are spectacularly bright. There's a very nice XKCD cartoon about this that sort of describes the fact that anything you can think about, any way you can try and conceive of the intensity of a supernova, you're always about 12 orders of magnitude off. So, for example, if the sun were to go supernova now, you would get a bigger radiation dose from the sun going supernova than from the biggest nuclear weapon ever designed going off on your eyeball. These are incomparably powerful. So they measure these distances and these velocities and discover that actually we're slightly off the flat line. The flat universe critical density is this red line, and oh, we're somewhere up here. And it's actually very nice, clean data, and there's a lot of it, and it's, it really is. There are these two experiments both doing it, so it's not just one experiment having these systematics. So now we discover that after all of that, the universe is accelerating. And there's no matter density that gave us an accelerating universe. So we're not even slowing down. It's not that we're slowing down, but just not fast enough. We're now actually accelerating. And that acceleration could potentially be driven by a cosmological constant. So we're back to Einstein. So they get the 2011 Nobel Prize. Meanwhile, on the CMB field, on the CMB side, we're working now with balloon experiments. Satellites are phenomenally expensive. But a balloon, a stratospheric balloon, you can fly up above the atmosphere, above most of the atmosphere. If you go down to Antarctica, you can fly these circumpolar missions. During the austral summer, there's a nice circumpolar wind. So you sit on the edge of Antarctica, send your balloon up. 2 weeks later, it's gone all the way around and come back overhead, and you drop it down again and get your data. So you get 2 weeks of observation from about 30 kilometers up. And there's a very nice complementarity here, which is very, very common in cosmology. The universe is an interesting thing to study because there's only one of it. So you have to be very concerned about variance. Or there's only one observable one of it. But if we can observe different aspects of it and look at the intersections of those, that gives us a much stronger handle, both for defeating systematics and for kind of breaking degeneracies between different parameters. So in particular, the CMB tells us about the geometry of space most of all, or at least one of the things it tells us, which is the sum of the amount of matter and the amount of dark energy, or cosmological constant. So this is because all mass energy gravitates. On the other hand, the supernovae tell us about the difference between those two terms, because the matter's pulling space and the dark energy is pushing space. So one tells us about the dynamics, one tells us about the geometry. Combine them together and we break the degeneracy. So here are the boomerang CMB results. This is the amount of matter in the universe as a fraction of the critical density. This is regular matter or dark matter, any kind of matter. And this is the cosmological constant as a fraction of the critical density. So this line here, omega matter plus omega lambda equals 1, is the flat universe in units of the critical density. And if we're this side of the line, then we have an open universe. And if we're this side of the line, we have a closed universe. And so we put these two sets of results together. Here are the Supernova Cosmology Project results, the boomerang results, and so we get a universe somewhere around here. And that's obviously been refined over the years, but suddenly we're in this strange place where it was an extraordinary thing when these results came out. Overnight, almost every cosmologist flipped from we know that the cosmological parameters are X, Y, and Z to we know that there's something completely different, but we know with just as much conviction. Which is, that's the way science is supposed to work, but it's kind of funny to see that flip. So we now have what's called the Concordance Cosmology. 70% dark energy, possibly cosmological constant. No idea what that is. 25% dark matter. We know that that has to exist because of the dynamics of galaxies and the difference between the measure of the mass based on their dynamics and the measure of the mass based on their brightness. We know that 25% of the universe has to be dark matter. No idea what that is. 5% of the universe is in ordinary matter. So we've got a good handle on that. So we have quantified our ignorance. We know nothing about 95% of the universe. So this becomes the driving question. What, and more particularly why, is the dark universe? And one of the nice things about, one of the really exciting things about this, it's a little bit like sort of 1910 theoretical physics, when all these results were beginning to come out that didn't quite fit with classical physics. So two-slit experiments, attempts to measure the ether, all these kind of things that were giving hints that classical physics wasn't working, and eventually led to the whole explosion in quantum mechanics and ultimately quantum field theory. These are the beginning observations that our standard model of the universe, which on some level is ultimately based on fundamental theoretical physics, particle physics, has these things in that appear nowhere in anyone's field theory equations. No one's writing in a cosmological constant in their field theory. No one's writing in dark matter. But somehow they've got to be there. So these are the first hints that this theory that is exquisitely precise for measuring any terrestrial experiment we can do, or even for measuring what we'd expect to see out of a supernova, for predicting that, works beautifully, but is clearly incomplete because there are these things that just have no place in the theory as it currently stands. So here's our history of the universe. We have a Big Bang. We have all kinds of quantum fluctuations going on that get inflated. So these tiny quantum fluctuations, during that exponential expansion, they get stretched so much they become classical. They get pushed outside of the causal horizon of the universe. And then as the universe expands and catches up with them, they seed these perturbations. We have the dark ages, where nothing much happens, just gravity slowly working its business, taking these seed perturbations and forming clumps out of them, big enough that about 400 million years after the Big Bang, you get the first stars forming. And then we have the whole evolution of everything since then, clusters of galaxies forming, the process of matter going through stars and all the heavier elements being formed from supernovae. And then, so you can see this represents the dynamics. So we're slowing down, and then suddenly we start accelerating again as dark energy becomes the dominant contribution to the energy budget of the universe. And so this is what we're now observing. So when we send up a satellite like Planck, we look back through time and we look back at this surface of last scattering. And as I say, this both tells us everything about what happened between the Big Bang and the surface of last scattering, but also what happens between the surface of last scattering as a sort of a backlight to the entire history of the universe subsequently. So we're really looking for two things in the microwave background. We're looking for these primary anisotropies, these seeds that have generated all the structure subsequently, coming in from the physics from the Big Bang to today, to the last scattering, and then these secondary anisotropies that generated since last scattering by all the matter and things going on between last scattering and today. One of the things that's fascinating to me about this as a field is that there's a whole sequence, pretty much everything that we have ever observed in the CMB. You look at the first theoretical paper predicting it, and it says, here's an interesting theoretical curiosity. There ought to be this tiny, tiny signal. Of course, no one will ever be able to measure that, but isn't that an interesting theoretical result? And 20 years later, that's what we're looking for. So the technology, the experimental and observational technology is always catching up with these things that were originally predicted as purely theoretical curiosities. And that's happening, and that happened as recently as a few weeks ago, that I'll talk a little bit about at the very end. As you might predict from that kind of background, if the signals that we're looking for are always considered to be so faint that they're purely theoretical curiosities, the challenge is going to be twofold. It's firstly going to be how do you detect these things? And as I'll show you, and what I'm going to focus on is once you have a detection, how do you decode from that to derive the science? So here's how we detect the CMB. We're looking for tiny, tiny, tiny fluctuations, micro to nano Kelvin fluctuations, on a background that's only 3 Kelvin to begin with. So we need a large number of very sensitive, very cold detectors. And so here are 3 experiments. On the top here is the polar bear experiment. It's obviously a ground-based telescope sitting high, somewhere very, very high and dry in the Atacama Desert in this case, looking out at the sky from northern Chile. Here's the boomerang balloon about to be launched in front of Mount Erebus at McMurdo Station in Antarctica prior to its 2-week flight around the pole on these circumpolar winds. And here's the Planck satellite up at the second Lagrange point. So it's Sun, Earth, second Lagrange point. The satellite sits being dragged around in the frame of the two, always with its back to both the Earth and the Sun. If it accidentally caught a bit of sunlight or even reflected off the Earth light, it would fry all the detectors because they're so sensitive. And it's scanning the whole sky and eventually building up a map like this. Obviously, the nice thing about space is you get to see the whole sky and you have no atmosphere in the way. The tricky thing about space is it costs you $1 billion a pop. So what do we see when we look at the sky? Well, we see something like this. Noise. And the great thing about this noise, I mean, these detectors are exquisitely sensitive. They are unbelievable. I mean, I tip my hat to the experimentalists, the people who build them. These are phenomenal devices. The particular challenge is that this noise is not white. This noise has long time correlations. So the signal that I see at any given time is affected by the signals that I have been picking up for the last 5, 10, 15, 20, couple of hours, some amount of time. So we can't just bin to reduce the noise. We've got to do something a lot more subtle than that. That's what I'll talk about. When we do that, we end up with maps of the sky, if we do that correctly. What I'm showing you here are the map of the CMB, the sky as seen by the Planck satellite at the 9 frequencies that Planck observes at. And it's important to observe at 9 frequencies because the microwave background, if you work in the reference frame of the microwave background looks the same at all frequencies if you normalize to a perfect black body. But the foregrounds vary significantly with frequency. So in these maps, the CMB is identical at all 9 frequencies, and anything you see that changes is foreground contamination. The nice thing about that is that we can use the fact that the CMB is fixed and the foregrounds change to distinguish between the two. And when we do that, we get a map just of the CMB. So this is the Planck map from the first Planck release. We've even been able to strip out the galactic plane by somewhere between sleight of hand and magic. So we have this picture of hot and cold spots. And you can see that there is a sort of a characteristic size. It turns out to be about a degree scale, a blob like this, about the size of the full moon on the sky. That's the dominant scale for these fluctuations. But you can also see that there are things going on big scales. There are big hot regions and big cold regions. And there are things going on much smaller scales. So what we'd like to do is characterize this in a way that tells us about the parameters of cosmology and also to get away from the fact that this is one realization. If we went to a completely different part of the universe and looked at the CMB, we would see a realization of the same cosmology, but the particular sky would be completely different because where the hot and cold spots were from some other vantage point would be completely different. So we want to characterize this in a way.
Even from the same vantage point, like it will change over time, right?
It would change over very long time scales, yes. Not time scales that we're going to be able to observe over. Having said that, that also complies, is consistent very nicely with what I was saying about every prediction about the CMB starts as being, there's an interesting theoretical curiosity, but we'd never be able to measure it. So my guess is that in 20 years' time, we will be measuring that.
So what kind of data is it Like, is it just a signal and you are doing FFTs on it? Or?
I'll come into this in detail. So we want to characterize this. The way we do that is to reduce it to an angular power spectrum. So we take a spherical harmonic transform over the sphere, and this top curve here is the spherical harmonic transform of that map. And so this is the, if we go into the spherical harmonics are characterized by their coefficients, the ALMs. We average over M because the universe is rotationally invariant. So we're just looking at what's the power on different angular scales. If I take 2 points in the sky separated by a given angle, what's the power on that scale? So here, around about the degree scale, multiple about 200, is the biggest peak. I can't reach. So that's that degree scale dominant contribution. But we can see that there are fluctuations on all scales, and in particular in that top curve, you can see there's a harmonic sequence of peaks and troughs, and that's exactly as you would predict from an inflationary theory. These other curves are measurements of the polarization of the CMB, and these are predictions of what Planck should be able to do. And so we have the temperature spectrum on the top, the temperature crossed with the E-mode polarization in the middle, the E-mode polarization, and the B. And so the particular holy grail now is to measure this B-mode polarization, and in particular these two bumps. This bump comes from the lensing of the E-mode polarization as it passes through all the matter between last scattering and us. So that's kind of interesting but well understood. This bump here is where the third Nobel Prize in CMB physics will be. And this is predicted from gravity waves generated during inflation. So inflation happens a millionth of 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 a second after the Big Bang, expands the entire tiny, tiny, tiny bit of the universe into the entire visible universe. And in that process generates gravity waves that leave an imprint in the B-mode polarization of the CMB. So a detection here would link together these physics at extraordinary. We'd be looking at the entire visible universe today to measure something that was happening 10 to the minus 36 seconds after the Big Bang on Planck scales. Planck, as in Max Planck scales, not satellite scales. So that would be an extraordinary thing. And there's recently been a claim of a detection there, which I will refer to at the end. So in order to do that, we have to gather more and more and more sensitive data sets. So there are two directions we're going in. We're getting into ever higher resolution. We want to see things on finer and finer scales. And you can see that by these 3 satellite missions. The COBE satellite, off on the far left, 10-degree beam, just see very big blurry structures on the sky, and they were mostly noise anyway. The WMAP satellite, it's the successor. So that measured with about half-degree beams, and get this. And Planck, which is measuring with 5 arc-minute beams, and getting down to this kind of structure and into polarization. And that then leads us to the challenge. As we're trying to extract fainter and fainter signals, the only way we can do that, our detectors are now photon noise limited. So it's not that we can make our detectors more sensitive, we just have to gather more data. And how do you gather more data? Well, you either have to use more detectors and look at the sky for longer. Both of those give you a larger and larger data volume. So we're having to gather larger and larger volumes of data, and we're having to do more and more precise analyses, because as we push to fainter and fainter signals, our control of systematics has to get more and more precise. So here we can see a range of experiments over the last couple of decades and going forward. And essentially what happens is that CMB datasets grow with Moore's law. We see a 1,000-fold increase in the data volume in 15 years, every 15 years. 15 years in the past, it was 1,000 times smaller. 15 years in the future, it'll be 1,000 times bigger. So that tells us a couple of things. Firstly, it tells us that all our analyses need to use linear, at worst log linear algorithms, because if there's any kind of power law in there, this is going to kill us. And secondly, we're going to have to sit on the leading or bleeding edge of high performance computing for the next 15 years, as we have for the last 15 years. So this is really a long-term program. What I thought, I'd come here for a couple of years and write the definitive CMB analysis package for massively parallel computers and be done? No. It's an ongoing challenge. And so I'm going to try and walk through in the little time left. So in theory, this is very simple. We can write down very, very simple Gaussian likelihoods for the map of the sky given the time-ordered data and the noise statistics, and then for the power spectrum of the sky given the maps and their noise statistics. These are very simple. It's a Gaussian likelihood. One of them I can even maximize in closed form. So I can write down a solution. The other one I have to use iterative methods, but no big deal. Except that it's not quite like that. In particular, the noise is correlated and colored. That gives us complications. The data are not ideal, despite the fact we keep asking experimentalists to build perfect experiments. They keep failing. They keep building beams that aren't exactly circularly symmetric. They keep building detectors that get hit by cosmic rays every now and then and get a big spike in them. There are these foregrounds to deal with. We can't, we try and tell NASA or ESA that we need to fly to the Great Void, just and do an observation from there. That's not happening. So we have to deal with all these non-ideal features of the data. And then the piece that I've been particularly involved in and focused on is how the algorithms and the implementations for doing the analysis have to change both with the increasing data volume and with the changes in HPC architectures. And those are two drivers, and if you ignore one of them or the other, you're going to be in trouble. So basically, this is why this is a completely ongoing process. Both of those things are evolving, and we have to keep evolving with them. So the challenge is that the exact solutions, we can write down these nice closed-form solutions. It's dense linear algebra. We get very high performance. It's nice level 3 blars. But it means it scales as the number of pixels cubed. So for the Planck satellite, we have 9 frequencies. Each frequency has 3 maps. Each map has a couple of 100 million pixels. So I'm going to be building something like a billion by billion covariance matrix and inverting that. That's going to be challenging. So we can no longer do these exact solutions. So you have to use approximate solutions. So we can solve for the maps using precondition conjugate gradient techniques. That just scales as the number of samples times the number of iterations in our PCG. We can solve for a pseudo-spectra, and I'll talk a bit more about these, ignoring all of the inhomogeneities and incompleteness of the sky, just do a spherical harmonic transform. That scales as the 3/2 power of the number of pixels, so we can manage that. Then the challenge comes down to the fact that we end up with a biased result. It's biased by the fact that we haven't got complete sky coverage, the galactic cut, despite that very pretty map. We don't include the galaxy in our power spectrum analyses because it's completely contaminated. And our noise is inhomogeneous, so different parts of the sky carry a different amount of noise. So when we just do the straight spherical harmonic transform, we get a biased result. So we have to debias that result, and we debias that result by using Monte Carlo methods. So we want to generate up to 10,000 realizations of the data. So we have one real data set to analyze and 10,000 simulations of the data. So we're completely dominated by simulations. And those scale as the number of realizations. We have to generate the data and map it. So it's another map making, number of iterations times the number of time samples. So this is how things have evolved with the boomerang data. We're running on a Cray T3E, the machine that was sitting on the NERSC floor when I first came here, 700 cores. We could do explicit maximum likelihood. We could solve both for the map and the power spectrum. We could even do Cholesky decomposition instead of explicit inversion. Great. This is what the original boomerang results came out of. Then we move forward to the follow-on boomerang experiment. We are now on an IBM SP3, much poorer communication fabric than the Cray. So we had to move from Cholesky decomposition to explicit inversion. There was just too much communication in the Cholesky. Then we moved on to the Planck, and Planck at single frequencies. We moved on to a 6,000 processor IBM, just doubled the existing machine. But now we were working on Planck data with millions of pixels in the map. Couldn't do the explicit methods anymore, so moved on to these PCGs and Monte Carloing to do the debiasing on the pseudospectra. That was running on about 6,000 cores. Then we started doing working on all of the Planck mission and on some of the next generation balloons and ground-based experiments, pushed up to about 40,000 cores on the Cray XT4. And now, I'll talk in more detail about this, but separating the simulation from the map making turned out to be the killer step. So we glued them together and now generate the simulations within the map making code and avoided all the I/O bottleneck. And finally, we're moving on to the XE6 to do the Monte Carlos for Planck and to do things like Polar Bear, which has 10 times the data volume of Planck. And now we have to hybridize our simulation of map making. That takes us up to about last year, and I'll briefly talk about where we'll go beyond this. So here we go in practice, going from a small patch of the sky with boomerang just for a temperature map, 10 to the 8 samples to 10 to the 5 pixels, Planck temperature only map, 10 to the 10 samples to 10 to the 8 pixels, EBEX, 10 to the 11 to 10 to the 6 on 15,000 cores. And here was an early Planck Monte Carlo, just Monte Carlo in the temperature, done on about 32,000 cores. So as I say, the challenge here is how we generate these Monte Carlo sets. The first time we ever simulated and mapped an entire Planck frequency was when NERSC took delivery of the upgrade on the IBM from 3,000 to 6,000 cores. And it turned out after IBM had sold NERSC the machine and it had all been installed, they suddenly realized someone had hard-coded the MPI version to have a maximum of 4096 tasks. But we had a 6,000 core machine. So no problem, SED minus I and replace 4096 with 8192 and that should work. So we update the MPI and so they want a code to run on the entire machine. So they gave us the entire machine to work on for a few hours. And in 6 hours work on the entire machine, we were able to generate one realization of the Planck data at one frequency. Great. We only need 10,000 at 9 frequencies. So when we scale up, we were going to go from 36,000 CPU hours to 3 billion CPU hours. Even my allocation at NERSC doesn't get that big. But there's Moore's law. So we take that into account between 2006 and 2012. That gets us down to 200 million hours. No problem. Well, our NERSC quota is more like 10 million. In fact, we pushed up a little bit, but it's of that order of magnitude. So we had two challenges. Firstly, and we knew this at the outset, firstly, how do we go through 4 epochs of Moore's law, however they might be achieved? And we've seen that the method by which Moore's law is maintained changes over time. Always has, always will. We have to follow whichever direction the computers go in. And secondly, we're still a factor of 20 or so off. So we better get something out of algorithmic and implementation speed up. So here we get into some of the more gory details. We're generating a simulation. The data is both noise and signal. And the signal is given by where you're looking at the sky at a particular time. So the P is the pointing matrix. Is there anything I can use as a pointer?
Your mouse, if that works.
Ah, you mean?
Yes, that'll be captured in the
Okay, great. So this thing here is just mapping where I'm looking. This tells me at time t, I'm looking at pixel p. So if I've got a map of the sky, a signal that's pixelized over the sky, I just have to say, well, at this time I was looking here, at the next time I was looking here, at the next time I was looking here, feed those into the time string. So to generate the noise, it's just pseudo-random number generation followed by an FFT. We generate white noise and then we color it. And to generate the signal, we just scan across the sky, use the pointing, and convolve the sky with the beam at every sample. So that's mostly spherical harmonic transforms. And then we want to do the map making. this rather convoluted equation here, but it's really just an AX equals B. And so we're going to build that, and solve. First we have to build the right-hand side. That involves taking the data, weighting it by the noise, and unpointing it from the time stream to pixel domain. And it turns out that because of the properties of the noise, we can do the matrix multiplication by going into the Fourier domain. And the matrix is diagonal in the Fourier domain. So we do a Fourier transform, a diagonal matrix vector multiply, even I can do that, and then an inverse Fourier transform, and that takes account of the noise. And then we solve for the map using PCG, and at every iteration we have to do again this Fourier transform, diagonal matrix multiply, inverse Fourier transform.
Is that a 3D?
No,
transform?
no, it's a 1D Fourier transform. So typically we would expect everything to scale just with the number of observations. You saw the nope. So we've got FFTs, we've got spherical harmonic transforms, which we've got FFTs built into them. And we've got a matrix vector multiplier where the vector is a time domain vector and the matrix is diagonal. So everything should scale with the number of samples. So it should scale linearly as we increase the number of observations, and it should scale arbitrarily to any number of cores, in theory. But of course, that's not the way things work. I/O turns out to be a real issue. As I'm sure you either know or have had many people kvetched you about. Calculation follows Moore's law. Communication is the poor relation, and I/O just trails somewhere way off in the distance. And so as you go to more and more advanced computers, the ratio between calculation, communication, and I/O gets worse and worse and worse. So I/O is a real issue. We have to read in the pointing data. We have to write out time streams, and then we turn around and read those back in and calculate a map and write that out. The maps are calculated, distributed over all the processes, and then have to be gathered together, so there's a communication there at each iteration. And we have calculation inefficiency. We have this problem that we move from these beautiful level 3 blars with lots and lots of data reuse and very, very high computational efficiency to linear algorithms, where by definition data is not reused. We can't afford to reuse the data. So we've got much, much lower computational efficiency there too. So basically those are the challenges that we have to address, and we have to address them anew with every new generation of architecture because the balance is different. So as I said, the big bottleneck that we first broke was the I/O bottleneck. Someone had written a simulation package, someone had a map making package. You generate the simulation, you write it out to disk. You read it back in and you make a map out of it. Well, let's just glue those bits together and avoid all that unnecessary I/O. So in the Planck case here, you see we would have anticipated ending up having to read about 500 petabytes of data and write 70 petabytes of data. Glue them together, do the same operations, but now every time the map making code says, go get me this data, there's an underlying data abstraction layer that says, hang on a minute, this data doesn't exist, I better simulate it. Generates a simulation and feeds it back to the map maker. The map maker never knows whether it's reading real or simulated data. It doesn't have to. That whole thing's been abstracted away. It just says, get me the data, and we pass it back. And that gets us down from the 700 petabytes to 2 gigabytes of reading, a much more manageable quantity. So we've got, and 70 terabytes of writing. So we've compressed the reading by a factor of 10 to the 8, and the writing by a factor of 10 to the 3. The communication, we've got this data spread over all of the processes. We have to divide the data in time intervals for load balancing, and because data sampled at the same time uses the same telescope pointing. And one of the big savings was, instead of reading in the pointing for every single detector, just reading the whole telescope's pointing, where the telescope was looking, and calculating the pointings of each of the detectors from that. So that compresses the pointing data by a factor of the number of detectors. So we really want to divide data in contiguous time slices and say, okay, process 1, you've got all of this data. Process 2, you've got all of this data, and so on. That means that the observations on the sky, the pixels, are distributed all over the system. So we have to pull those all together at every iteration. And because we're lazy, we do that by an MPI all reduce. So we take the local data, zero pad it out to a full map, do an all reduce, and then just pull out the pieces that you're interested in, each process is interested in at the end. Easy to code, very painful to run at high concurrency. Obviously, much better ways of doing that. Firstly, we can reduce the number of MPI tasks by only using MPI for off-node communication. So this is where we hybridize the code, threads on the node, MPI off-node. And secondly, so that reduces the number of tasks and communications. And secondly, we can reduce the total volume of the messages by getting rid of all this zero padding. So for every pair of tasks, you calculate the pixel overlap, and then at every update, you just communicate the information between that pair of tasks that is common to them. So that's essentially this. Now it turns out that if you're looking at a small patch of the sky from a suborbital experiment, then in any given interval of time, the data in a particular time interval covers pretty much the whole patch. So in that case, it's still worth doing all reduce rather than calculating these overlaps, because the overlap is pretty much the whole patch. If you're doing the whole sky, it's not the case. So we have these two cases depending on the distribution of the data over the processes. So here are the results. This orange dot at the top, this was the heroic run on Seaborg when it first became 6,000 processes to prove that MPI worked.
So the axes, a little hard to read that.
Sorry, this is the number of cores running from 1,000 to 100,000 logarithmic scale, and this is the seconds per realization from Monte Carlo, also logarithmic scale, ranging from 10 to 100,000. So that orange dot, that's about 6 hours on 6,000 cores. We then moved to Franklin and moved from separate simulation and map making to a combined sim map. So the simulation is only generated during the map making. And you can see now we gain a huge factor, more than an order of magnitude on the runtime just by avoiding the writing out and reading in again. But we don't scale very well, because as we get to larger and larger concurrencies, running MPI all reduce over 40,000 cores turns out to be not a smart thing to do. So then we go to this final case where we've both got the joint simulation of map making, and we've threaded it and moved from an all reduced to an all-to-all kind of scat together. And these are these three curves, and I'll talk about a bit more why I'll talk more about why there are three of them in a moment. But this gets us down from, so we've gone from 6 hours to a couple of minutes. So it's kind of a nice reference point for me. You know, the first time we ran this was the heroic prove that Seaborg works with the new MPI over 6,000 cores, run for 6 hours. Now that same job is our sort of small debug, couple of minutes, check that the code's working kind of job. So,
Question, has the bottleneck then moved somewhere else?
yes, answer to come. So yeah, we have an interesting situation now because systems are getting more and more heterogeneous. So for example, these runs that I was showing you were done on NERSC's Hopper system. It's an XE6. So a little over 6,000 nodes, each with 24 cores. It's a very nice machine. However, those 24 cores are divided into 4 NUMA nodes, each with 6 cores and its own memory block. Now, technically, the memory is shared across all the NUMA nodes, but the width of the line here reflects the fatness of the pipe connecting to that bit of memory. So local memory, very, very, very fast access. Your nearest neighbor's memory, well, it's slower. And if you start going crossways, it grinds to a halt. very, very different. So these are these non-uniform memory access, NUMA effects. So the question is, what's the best way to run hybrid code on a system like this? And this is where these three plots come in. So the blue line here is running 4 tasks with 6 threads each. This is the NERSC recommended way of running. Run a separate task on each NUMA node. You avoid any NUMA effects. You're only ever accessing local memory. It's all great. So you can see out at the low end, the 4x6 is the fastest. And remember, this is a log plot, so those differences are very significant. The red line is running 2 tasks, each with 12 threads. So that means only ever accessing nearest neighbor memory. And the final case is running 1 task with 24 threads. So that means you could access any bit of memory anywhere. It's going to be a mess. And so this is the impact it has at low concurrency. However, the downside to running 4x6 is you've now got 4 times as many MPI tasks. So when you come out to the high concurrency and you're running on 150,000 nodes, suddenly your MPI is killing you at 4x6, and the best way to run is 1 by 24. So at very high concurrency, you need to run with as few MPI tasks as possible, and at low concurrency, you need to run with with as little non-local memory as possible. So now we have an interesting kind of challenge in running on a system like this, of having to know how it's going to behave with data at different data volumes at different concurrencies. You can get into attempts to do real-time performance tuning, auto-tuning, or you just learn from experience, try a few experiments, and say, okay, well, if I'm running out here, I better just bite the bullet and take the NUMA hit, because otherwise the MPI hit is going to kill me. So we ended up running sort of in this kind of region. It's typically hard to get the whole of the system at once, and generated the full focal plane 6 simulation set. So this was absolutely key to all of the 2013 Planck results. Generated 1,000 realizations of the entire mission, and turned those into about 250,000 maps. So this was the Monte Carlo set for all the other analysts to use. 250,000 maps, because you want to divide by frequency, you want to divide by different surveys, you want to cut the data, do first half, second half, so you can do systematics tests on differences. We want to use subsets of detectors at each frequency, so by the time it all expands, you end up with about 250 maps per realization. And so on the right-hand side here, I'm showing you the temperature and polarization maps at the 9 frequencies. There's no polarization at the top 2 frequencies, but again, you can see how the foregrounds change with frequency. You can also see very clearly, well, and even more so in this, these patches here, here, and here are the ecliptic poles. So Planck is scanning around the sky and then rotating as it scans, but it's always going through the poles. So these 2 regions are very, very low noise, because every scan of the sky covers them, whereas regions in between are much noisier, because only certain scans cover them. That's this inhomogeneous noise I was talking about, which is why you can't just take a spherical harmonic transform of this. So that little movie in the bottom, that's 1,000 realizations of the Planck noise at a particular frequency. And you can see all kinds of things in there if you let your eyes fade. But you certainly see very clearly there's an H-shaped structure here from the scanning strategy, and a cross up here. And if you've got very good eyes, you can maybe see there's a ring across here that was it's called the day that Planck stood still. We scanned for a whole day on a single ring rather than rotating. So it's got slightly less noise. But if you don't feed that information into the analysis, the subtlety and the faintness of the signals we're looking for is so extreme that you will get completely the wrong results if you don't deal with things at this level. But instead, we got the front cover of the New York Times, 28 papers released by the collaboration on the one day, probably about 2,800 released by other people since then. And we have this very interesting result. You know, we can fit all of the cosmology we can see with Planck with 6 parameters. It's an extraordinarily successful model. We don't know why those 6 parameters have the values they do. Ultimately, you'd really like to have some underlying theory that predicts them, but we can characterize. There was some tension with previous results. We've got a little bit more dark matter, a little bit less dark energy at the 1-2% level. Moved the Hubble constant, this expansion rate, by about 10%. The ratio between the scalar fluctuations generated by these density perturbations and the tensor fluctuations generated by gravitational waves during inflation, we predicted to be less than 0.1. And then there were some interesting things about whether the northern hemisphere was statistically different from the southern hemisphere, whether there's a big cold spot. You may have seen in about a month ago now, BICEP2 announced its first results, and it announced that this scalar to tensor ratio was 0.2, much higher than anyone expected. Most of the experiments that were being built to eventually detect this were targeting 0.01. And inconsistent with Planck, but I put inconsistent with an asterisk because theorists are very nimble. And so already there have been a number of papers coming out explaining how if you twist cosmology slightly, we can make it consistent with both BICEP2 and Planck. And as I said before, the detection of this bump, this gravity wave bump here in the B mode spectrum is anticipated to be the 3rd Nobel Prize for CMB physics. Here's the lensing spectrum. So this is, remember, the lensing of the E modes, and this is from fundamental physics going on at inflation. And so what you measure is the sum of those two. And here are the BICEP points. And so there are many, I think if you took a straw poll of cosmologists, no one actually believes this result, except for the BICEP team. In particular, the data here look very high, especially when about a week before they published the polar bear experiment that I'm on, put these points on the plot. So we're detecting the lensing signal very, very nicely, just where we expect it to be. You don't really get to play with this very much because it's derived from the E mode signal by lensing. We have a pretty good idea of how much matter there is in the universe. Planck has actually mapped the whole lensing potential. So this pretty much has to be here, and yet they're missing it very significantly over here with 4 points in a row. One of the issues that they have is that they only measure at a single frequency, so they can't do this separation between foregrounds and the CMB that we can do with the 9 frequencies on Planck. So if you press them, they will admit that R of 0.2 is really an R effective. It's the total signal in the patch of sky they studied that would be a mixture of the microwave background and the foregrounds, and they think the foregrounds are small. Planck will have very nice foreground separation later this year when the first Planck polarization results come out. And just to wrap up, what have we got coming? To come back to your question. Well, the current suborbital experiments are generating 10 times as much data as Planck. The next generation will gather 100 times, and the big projects currently going before funding agencies for review and possible future fielding will generate 1,000 times, and that's the 1,000 times is what you need to really be able to characterize this B mode signal and pull out all of the physics. We can measure the mass of the neutrino from this signal. It's extraordinary, this idea that you could measure this signal that was considered to be unmeasurable when it was first proposed, and use that to measure the mass of the neutrino, something else that was considered to be unmeasurable. But we can do it. The universe is the ultimate particle accelerator, and so we can use it as that. On the other hand, as that's happening, we know that the next generations of supercomputers are going to get harder and harder to use, more and more interesting and challenging to use. Huge core counts, even if some of those cores are wrapped up in units that you sort of have to think of as a single unit. increasingly heterogeneous nodes. We've already seen this with nodes with accelerators attached, but there are already designs, particularly coming on to this last point about increased constraining power. We're seeing designs with potential for dark silicon, with things that turn on and off depending on when you need it. And so how you code for a very different, very heterogeneous kind of node and kind of architecture we've got a couple of different generations of accelerators, but then who knows what comes in the generations beyond that. So just to conclude, I would say that we have this extraordinary window on the universe. As I said, these photons capture the entire history of the universe. The way they capture it is in very, very subtle, hard to detect signals, but it's there. Because the signals are so subtle and hard to detect, data analysis is absolutely a computationally challenging problem and will require us to stay on this bleeding edge of high performance computing as we have been for 15 years and going forward for the next 15. And that both the data sets and the systems we're using to analyze them are evolving. And we have to stay with that dual evolution. There is no sort of end point. And because they're both changing and changing essentially completely independent of one another, we're sort of caught in between the two, being pulled in two directions at once. And so that's the path we have to tread, is the midpoint between these two pulls. But the science we can extract is extraordinary, and ultimately will only be limited by two things: by our computational capacity and capability, and our ability to exploit it. And we used to just sort of really think about this one and just assume that it was going to be straightforward to exploit it. And I think it's clear, and I'm sure other people have talked to you about this. This is no longer the case. It makes it a very exciting field, but also a little daunting at times. Thank you.
So, any questions for the speaker? I have one. So what's the bottleneck now?
So it depends on the system we're running on, and it depends on the data set we're running. So the I/O we've basically solved. The focus for a lot of the challenge at the moment is exploiting accelerators. So bandwidth to a GPU, for instance.
So to do which part of it, the PCG or?
The Fourier transforms we were thinking would be an interesting first stopping point. Now it turns out that what we really want, because our Fourier transform involves taking a sky vector, unwrapping it to a time domain vector, Fourier transforming it, multiplying it by a diagonal matrix, inverse Fourier transforming it, and then mapping it back to a sky vector. We should do all of that on the GPU. So we want to just be sending pixel domain data objects, not time domain data objects. But that means we have to wrap an entire kernel, program a whole kernel to go on the GPU. So as a first exercise, we just tried shipping off the FFTs. And no big surprise, it could do the FFT screamingly fast, but sending the data back and forth was a royal pain.
And if the prediction of the third Nobel Prize is true, who will win?
That's a very good question. So that will depend on
And will we need more parking places?
So a lot will depend on what happens with these results. So the interesting thing here is that the error bars here are tiny. And this was announced as a 7 sigma result. So if you went down to R of 0.1, which is what people are thinking is probably more likely, that's more than 3 sigma away from the current observation. However, then you start getting into politics and publicity. So interestingly, there are no papers. No papers have been submitted with these results yet. They've just had the press conference to announce them.
If there are no more questions, let's thank the speaker again.